Thank you for the introduction. So this work is done with my former PhD student, Dr. Lianing Zhao. Unfortunately, he could not come here because of visa issues. There was this government shutdown in the US, and he became a victim of that. So in this paper, we designed and implemented a solution using trusted execution environments, and we try to address two problems. One is very familiar to you guys and maybe to general public as well. That's the threat from ransomware. But at the same time, we also want to address this other threat, which is known as data destruction malware, or sometimes called wiper malware. Probably the most well-known ransomware is this WannaCry, which came about in 2017 and infected around 300,000 machines around the world. And that's shown in the red map there. But it also resurrected actually last year. It came back in 2018. The other one that I want to highlight is probably not very well known. It is called NotPetya, and it is really not a ransomware, even though it behaves like a ransomware. It asks for a ransom, but if you pay it, you are not going to get your data back. And there is a very interesting Wired article. You can read it, the damage that it caused. They called it like the most devastating cyber attack in history. And this kind of data destruction attacks are really not rare. Even earlier this month, there was an attack against an email provider in the US. And last year in December, I think there were attacks against energy companies in Saudi Arabia and UAE. And if you're old enough, you might even remember the CIH virus from 1998. It used to destroy some parts of your MBR and BIOS in some cases, just to make your machine inoperable. And of course, there are some solutions, because this is not a very new problem. The first one is you can back up your data. You can use some online service, or you can do it with an offline disk that you have. For online services, if you get infected, then slowly the malware can actually infect your saved online data. On the other hand, if the online backup service itself gets compromised, then a lot of users will be affected at the same time, which is a scenario we really don't want to hear about. But actually, it happened for some web hosting companies that they got compromised and got infected by ransomware. If you use your own disk to back up time to time your data from a local machine, that's good. But if you have resident malware, if you plug that disk in, and that malware can actually also start to encrypt or delete data from your backup disk. You can also rely on antivirus software, which can help you detect some of these threats. But if you are infected before there is a signature, then it's not going to help you a whole lot. You can also use solutions that monitor file I/O activities, just to understand if you in case got infected by a ransomware which has some kind of a fingerprint that they read your data, then they overwrite with encrypted data and delete the original one. So, but some other regular programs may also behave similarly, and it's not always foolproof to detect these activities. The last one I want to highlight is you can also save the encryption keys, file encryption keys in your system, so that if you ever see the ransom note, you can go back to the saved database and try to find out the corresponding encryption keys. One common problem for all these solutions is that they all rely on the trustworthiness of your operating system, which may not be very realistic currently. If you get infected by a rootkit ransomware, then all bets are off. There is a very interesting solution that was proposed in CCS 2017 called FlashGuard, and they rely on intrinsic write properties of SSDs to create some implicit backup of your data, and they can also handle privileged ransomware. But they require you to modify the firmware of your disk, and they cannot handle data destruction or wiper malware that I mentioned before. And that's where we come in. We propose this Inuksuk solution for data loss prevention against privileged malware, be it ransomware or wiper malware. And I want to highlight something from the very beginning about the scope of our proposal. we protect your existing data, meaning that, at the time when you get infected, after the infection, there is no guarantee. We cannot protect your data after infection. But the malware cannot delete or encrypt the existing data. That's the guarantee that we try to protect. And our solution relies on trusted execution environments from the disk and from your host CPU. And I'll elaborate on both of them. From the disk side, what we need is a fine-grained access control in a programmable way. What I mean by fine-grained access control is that, so you may have multiple partitions on a disk, and each partition we should be able to provide read access. We should be able to control the read or write access. For example, there could be a partition where anyone can read. There is no authentication or any access control for reading. But if you want to write, then you have to provide an authentication secret. You can have other partitions where anyone can read and write, and there is no restriction. And we want this protection in a programmable way so that we can lock a partition for writing for some time, unlock it, do something, do some write operations on it, and lock it back again. Any of these self-encrypting drives, if you might be using one, they satisfy our need. They do more than what we need, but these are the only things that we need from them. From the host CPU side, we need this dynamic root of trust environment because we run our trusted updater from a live operating system. We don't want to reboot the system, so we need this dynamic root of trust so that we can establish a trusted execution environment after the system boot. And we also want to control the write operations using an authentication secret, which we want to make it platform bound so that we can access it only from the same software and hardware, not from any software. Any modified software cannot access it. And we can get it with TPM sealing. The last one we need is device access from our trusted updater, because we have to access the disk, and in some cases we also have to access the display and keyboard. So we need this device access. And all these three can be satisfied by this Intel Trusted Execution Technology, or AMD's SVM with a TPM. You might be wondering that, okay, why not SGX? The first two can be satisfied with SGX, but not the last one, because it's user-level enclaves, and they cannot provide you direct access to the devices. You have to go through the operating system, and in our case, we don't trust the operating system. So in our design, just the very first overview is that we have a protected partition where we want to control the write operations, and the authentication secret, we need to protect it from the operating system, and we protect it with the host CPU's TEE. And what this design will allow us is that we can read and recover from any machine. Even if you are infected, you cannot access your machine anymore. You just take your disk to another machine, and you can read our partition. But for write or update, you need the authentication secret. I want to clarify here that the authentication secret that we are using, this is not a password. The user does not have to memorize anything. The user does not have to expose anything. When they are in a phishing attack or any other mimicry attack, they don't know any secret to leak. A little bit more about the design. So we have unprotected system or user data partitions, which can be accessed by your regular operating system and applications. They operate like before. There is no change for them. But we have this protected partition where only our trusted updater can access. And your applications and operating system can read data from that protected partition, but they cannot write anything to it. If you want to write something to it, then you have to go through our Inuksuk updater. And if you run an unmodified Inuksuk updater, then it can unseal the SCD secret from the TPM and then use that secret to write your data to the protected partition. So if you have a new file, it will write it like that. If you updated a protected file, it will just create a new version without deleting the old one. And when you are done, you just return control to the operating system, and the OS will run as before. You can deploy it in two ways. The first one is in a standalone mode. In this case, you have the user must have an Inuksuk capable machine, meaning that a TXT CPU with an SSD drive. And in this one, there is no other dependency. The user can use it the way that she wants. And so the user will initiate this Inuksuk program maybe twice a day or 3 times a day. And in between, whatever files have been accumulated, they will be written when you are initiating Inuksuk. So it is important not to, not to start Inuksuk for every autosave or every off now and then, because the TXT environment is exclusive. When you go into our trusted updater, the operating system and all your application processes, they are frozen. They are not active. So the user workflow will be affected. So you don't want to run it again and again and again. So you can run it like a Windows updater program maybe twice or 3 times a day. If you deploy it in a network-based system, and in that case we push the Inuksuk system behind an enterprise backup machine, and user can use any machine, any devices that she likes. They don't have to be Inuksuk capable. And the user or the system admin of the backup server, they can identify which files are really sensitive, which files are so sensitive that they are willing to pay ransom for. And then Inuksuk will come periodically and copy those files to the protected partitions. And in this case, there is no interruption for the user at all. A user will not even see that this system exists. We implemented this system on both Windows and Ubuntu. There were several challenges for implementation of this system. You can read about it in our paper. I just want to highlight the source of these challenges. So the trusted updater that we run, it has to initiate from a live operating system. So you have the live operating system, then you are freezing it, you are going to this trusted updater in this trusted execution environment, you are copying the protected files, the new files, to the protected partition, and then you have to come back. After coming back, you of course, you want to make sure that the OS is still active. OS can continue its operation. So the OS has no idea about what you are doing in this trusted updater, so you have to make it happy, so that, meaning that you have to save enough states and restore them just before you give control back to it so that it can go on. So that is not so trivial. The other problem is when you go into this trusted execution environment, we have no operating system. So you have no drivers for accessing the disk or any other devices that you want, so you have to handle all those situations. In terms of performance, we measured the file read-write access from our trusted updater when we are copying from unprotected partitions to the protected partitions. So the numbers are not great. They are sort of okay. So we achieve around 50% performance of your regular file systems. The reason is, one obvious reason is we are using FAT32, and it's not very efficient. And we could not use a more efficient file system because they are heavily tied to modern operating system. It's not easy just to take them and use them as a standalone. But the important thing is the slowness is affecting you only when you are copying new data from unprotected partition to the protected partition. When in your regular operation, when you are running just the operating system or your other applications, they run as fast as before. They are not affected at all. In conclusion, I just want to highlight the summary. So we designed this Inuksuk solution for wiper and crypto ransomware, and where this kind of ransomware or malware can have rootkit level access. And in our design, we used TEEs from both the disk and the CPUs. So this kind of multi-TEE based solutions can help maybe in other problem areas. And thank you for your kind attention. I'll be happy to take questions now. Thank you.
Again, if you have questions, feel free to come to the mics. So I have one question.
Yes.
So this is against kind of a ransomware that has this high privilege. like that
Right.
may compromise the OS. Is it based on some observations that there exists some this kind of a strong adversary model ransomware, or just curious how attacks are developed in the wild?
Yeah, so most ransomware programs are, user level permissions are enough for them. They are not rootkits, but there are some examples in the past that they came with rootkit level privilege. So we can handle both. So our solution is not only for rootkit level ransomware, it can handle just user level ransomware as well.
Fair enough.
Yeah.
Question, please.
Yeah, Suzaki from AST. So I have a simple question. I want to know the usability. So is it easy to use Inuksuk? So I want to know, it is used as a normal file system. Is it used as a normal file system or not?
Yes, so we do not modify any applications or the operating system. So it can be used. So for Windows and Ubuntu, you can use it as it is. The only problem would be usability-wise is that when you are using it in the standalone deployment, then time to time your normal operations will be hindered. You don't have access to the operating system when Inuksuk is running. So that would be the problem, in a standalone case. But if you use the network-based deployment, then you are not affected.
Okay, thank you.
Okay, then let's thank our speaker again. Thank you.